Well, hello, welcome back to part 3 of our unit on forces, and this will be probably the last one that I will consider really part of the motion unit, because we're talking more about acceleration. So just to remind you, in the first part, kind of describe just what acceleration means. To put it briefly, the rate at which you change velocity, okay? And then in the second unit, we looked at how to find the acceleration of an object by using information from a position graph. And that was a little involved. You had to find the slopes of the position graph just to figure out your speeds before and after you accelerated, and then use the acceleration equation, the difference in those velocities divided by how long it took to change, and that's how you got your acceleration. Now in this lesson, we're going to look at another kind of graph. Instead of position graph, we're going to look at a velocity time graph. And it turns out you can also see acceleration on a velocity time graph. I'll show you one of these in just a second. But it's much easier than doing it on a position time graph. So let me write kind of the key idea here for you to get down, and then I'm going to go to another screen. It's going to be hard for you to draw what's on that screen, so we'll get this down here. So, bad pen here. Let me see if I can fix that. It's a good reason to not leave your marker open all night. So here's what you're going to need to know. On a velocity time graph, the acceleration is equal to the slope. So think about now what we've seen. There's two different kinds of motion graphs, a position graph and a velocity graph. And each one has a slope, but they mean different things. On the position graph, the slope meant velocity. But on a velocity graph, the slope means acceleration. Okay? Now just to remind you again, what slope means, you have to find 2 points on a line to find a slope. You cannot do it with 1 point. That's a common mistake. You find the vertical separation between the 2 points. You just look along your vertical axis, how much are you going up or down? And then you look along your horizontal axis, how much are you going over? I call that the rise and the run. You could also write it a little bit more involved, the difference in your y values divided by the difference in your x values. But those are just other names that mean rise and run. Okay? So let's take a look at a velocity time graph, and we'll talk about what the acceleration looks like there. Okay, so here we have a velocity time graph. You see how it's labeled. It's got 3 segments on it. They've called them A, B, and C. I didn't make this graph, I just found it. And so there's 3 different slopes there. Now, it's important that you see that we have little line segments, each of those. So they each have their own individual slope. Now, what's the easiest slope to find there? I hope you recognize that a horizontal segment means it has no slope. It has a slope of 0. But the other 2 have different slope values. So let's find the acceleration during the first 2 seconds here. That's part A. And then we'll find the acceleration during the last 3 seconds, between 5 and 8. Okay? So I'm going to go back to my page here, and we'll say example number 1, slope during part A. Again, this is going to be kind of weird, because when you look at your notes later, you're not going to see the graph that goes with this. So this doesn't make a lot of sense if you don't have this video going along with you. So we always want to write the formula. So I start this way, rise over run. Again, you can use the other form if you'd like to. And then back on this graph, let's look at the slope during this part. So we start on 0, 0, and we go up here. So we're looking at the rise. How much do we go up during segment A? We start at 0, we end up at 30 meters per second. So that's a rise of 30 meters per second. And what's our run? It's how far over we go from the beginning to the end of that segment. We go over from 0 to 2 seconds. Okay? So that means the rise is 30 meters per second, and the run is 2 seconds. So if we divide those, we get 15, and what I hope are kind of familiar units for acceleration, meters per second, or meters per second squared. Okay? By all means, you can rewind and go back and look at that graph again. Example 2, slope during B. And I'm not going to have you show work for that because it's just 0 since it's flat. I don't want to take time for that. But during part C, again, always write out the formula with words or letters. Whoops, look at that. It's rise over run. Almost wrote it upside down. That's what I get for talking while I write. All right, and back to the graph. So now, again, be careful that you're picking 2 points. I like to find points right on the corners of my grid. So here we're starting at position, or at velocity of 30, and we go up 2 of these blue boxes, which gets us up to 50. Now don't just count boxes. It's not up 2, it's up 20, okay, from 30 up to 50. And what's our run? Well, we started at 5 seconds, and we go over to 8 seconds. That's a run of 3 seconds. All right? So a rise of 20 and a run of 3. So that's 20 meters per second over 3 seconds. You can grab a calculator if you want to, but I can do this one. Round off to a couple of digits here. That's 6.7 meters per second squared. Okay? So a little less, right? Actually, it's a fair amount less, isn't it? A little less than half of the slope. So that's how we see acceleration on a velocity time graph. It's actually a little easier, certainly, than what we did on the position time graph. Let me pull that up if you need to maybe freeze the screen there and jot things down. All right. Okay. So that's really all there is to it. Do watch out for negative slopes. I didn't show you an example of negative slopes, but anything that slopes down and to the right is going to be a negative slope value. And that just tells you that the acceleration is negative. Okay. So, all right, I think that's going to do it here. And if you need more help, by all means, ask the teacher for some help. Thanks for watching.